Hello everyone, welcome to another math team video. This time we'll be going over match 1 round 2 from 2019 and we're doing question 2. Alright, so the question goes, let's read it and maybe figure out some key points. So the variables are m and n are natural numbers such that they live in the inclusive range from 1 to 100, and when it says natural numbers, that means it's basically a whole number, and then we can see the constraints are right there. Alright, so the question is, how many distinct ordered pairs mn solve the equation m squared minus 4n equals 1? So this is very much a kind of number theory type of question, and let's just see what we might be able to figure out about perhaps the features of this equation. Alright, so the first idea you might get is like move everything to one side and then solve that quadratic, but that doesn't actually make any sense because there are two variables there, not one. So to actually do this, maybe we can move them to different sides and see what we get. So we get m squared equals 1 plus 4n. Now, this is already a lot of key information. So first of all, it's kind of like squared for m. So it's kind of like a square number equals, or you could also call it like a perfect square because it's a natural number. So this perfect square, m squared, equals 1 plus 4n. Now, the 4 here is very interesting because if you think about, the multiples of 4, all of them are going to be, even numbers, right? Because anything that's like a whole number times 4 will be even, because 4 is equal to 2 times 2. Alright, so definitely in the prime factorization of 4n, we would have, at least a 2 in there somewhere. And then here, the plus 1, or 1 plus, there it's kind of saying, well, this whole thing on the right side is actually an odd number. So the thing on the right has to be odd. That's kind of a condition that we get just from knowing that n is a whole number, a natural number, from 1 to 100, and multiply by 4 makes it even, plus 1 guarantees that it's odd, because any even number plus 1 is odd. So we can write that as a rule here. Maybe you can remember that. It's kind of like obvious once you think about it, but you might not really remember that it's important at many points in solving the competition problems. So we can say like even number plus 1 is odd. Alright, so the right is odd, and what does that say about the left side, m squared? Well, to get an odd number, you have to square an odd number. I think that makes sense. Because if you square an even number, you'll get an even number in the ones place. So that works with 1, 3, 5, 7, and 9. Basically, you'd have 1 here, you'd have a 9 there, and a 5 here, 9 here, and 1 there. So all of these and their kind of squared counterparts, let's say like this is x and this is x squared. And this is all, of course, in the 1 place. I guess you could mod 10. That could be like the operation here. But basically, that actually is kind of important. When you take the remainder of one number divided by another number, you get the remainder. And if you use 10 as the dividing number, then what you end up with is actually the same thing as what's in the ones place. Alright, so that's kind of a side note, but basically we know that m is odd, so we know that m is odd. Let's see, what else can we kind of figure out here? So m is an odd number, and then how many actually fit into that criteria? Well, let's think about this. So we've kind of reduced our space down to like 50 numbers. How can we reduce it further? Well, 4n plus 1, what is that kind of saying? Well, if 4n plus 1 is a square number, what does that say? M squared is on interesting. So let's look at an upper limit. This is kind of the next step. I actually don't know how to solve this problem. I forgot, but we can go along, right? So the maximum value for n, of course, m squared, the maximum value for the right side is going to be 400 plus 1, right? Or I should write it like this. Max value for either side is equal to 1 plus 4 times the maximum value for n, which is 100, equals 401. And already at this point, we can kind of see that m squared, it's not really going to be helpful for our upper limit, because obviously 100 squared is 10,000, and that's a lot of numbers. But now we kind of know the restrictions for m, so we know that, you know, if you memorize the square of the integers up to 20, so 20 squared is 400, so that's kind of an upper bound for m, or I should write n max value, and then m max value. So there's going to be 20. Alright, so on one hand we know that m squared is kind of stuck because of 1 plus 4n, but also we kind of are restricted to just having, you know, 1 through 20 as our, what's it called? 1 through 20 as our values for m. So that really helps out. And we know that if we're looking for pairs, there would only be one actual answer per m. So at most we have 20 pairs in total, because it's restricted by either one. Or it's restricted by both of them at the same time, but also you only need exclusively one. Alright. 20 pairs, but really, if you think about it, from 1 to 20, we only care about the odd numbers, again, because of our first rule. So we go down here, and now we actually only have 10 numbers. We have 1, 3, 5, 7, 9. You can just list these probably. 11, 13, 15. But also it's important, like, which ones actually work. That's the problem. 17, 19. Now, I don't know if there's anything else to do at this point, but the lower bound, of course, is 1 cannot be used, obviously, because the minimum value for the right side is 5. And then 3 works. 5 works. 7. 49, 48. Okay, that works. So I'm starting to notice that a lot of these work for some reason, and I'm kind of curious as to why that actually is. Actually, I think all of these work for some reason. 2, 2, 5. Wait, why do they work? Okay, so this is kind of like if you were doing the competition, you would just like go along with whatever's going on here. But it's interesting to see like why is it that this is the case. Why does this work? And by the way, I guess we have 9 answers then. So you would have to write the answer 9. Because it's not actually asking you for the values of the pairs. It's asking you for the number, how many actually solve this. Huh. Interesting. Is this just generally true? Interesting. Maybe there's some sort of thing you can do like m plus 1, m minus 1, that type of thing, equals 4n. And is this true for everything? Not really sure how to prove that. Ah, I see. Wait. Okay, so m plus 1 is even. M minus 1 is even. 4 times n is even. But what's important here is actually that there's a 4 here. And 4 is like 2 times 2. And an even number, any even number will have a 2 inside of it in terms of the factors. So 2 is a factor here and 2 is a factor there. So basically, when you multiply these two numbers together, the factors will be, the prime factorization will be at least 2 squared times whatever. And that equals 2 squared times n. And, you know, as long as the other factors are less than 100, that should actually work out. So that's very interesting. And we can actually prove that for a lot of these numbers, it's going to be less than 100. And how we know that is, well, m plus 1, m can be at most, 19. So it's at most 20. And then here, it's at most 18. So then you take the 2's out of them. Just take 1, 2 out. And you get 10. And then here you get 9. And then you get 90 times 90 as the thing over here, the dot, dot, dot. So n must be covering that range because it's like the maximum value is what's it? It's not is 90. So n kind of covers that perfectly. So we actually can just demonstrate that for any of these, it will work out as long as m is less than 10 or less than 20. Yeah. Okay, and by the way, when I say 20, I mean like the whole term, like m plus 1 term, and 18 is the m minus 1 term. So this actually does prove itself. I never really thought about that before. But anyway, the answer is 9. You could have just stopped after, the step of just saying that they all actually match. But the additional proof, if you were to think about it, like move the 1 to the other side now, then you could actually figure it out. Alright, so let's go over the key principles we used here. So first is move the variables to different sides. And then it's actually figure out some constraints here for the number theory problems. So, the oddness, evenness, that's kind of a common thing. There's also the maximum value for either variable. you can work that out, or the minimum in case that's more convenient. And after that, you might have to do another additional step of algebra where you kind of see some sort of pattern. And the pattern I saw after a while of thinking was moving the 1 back to the other side. Although the hope is that after you set your first couple of constraints, after the initial step of moving the different variables to the different sides, is that after you do that initial constraining, you'll be able to have a small enough range that you can just brute force it very quickly. And you saw that for me to figure out the kind of move the 1 back to the left, that took a while. So I was just kind of curious about what would actually happen, but to solve it quickly, you could just list out 10 numbers. Also, it's kind of like Sudoku because like the more you get correct, the easier it is, oftentimes. So for example, I first got, we got the max value of n is 401. Therefore, maximum value of m is 1 to 20. But then we use the initial constraint of m is odd, and then that reduces our number of pairs to at most 10. And then out of these 10, we can just list them out, and it works out. I don't think they can really come up with anything too much harder than this kind of problem. But definitely these principles are required. So first is constraining, looking for things like odd, even, max value, min values. And also not falling into the trap of maybe moving the 1 to the same side as the other variables. So I guess the principle is just move variables to different sides and then see if that helps you. Also remember, your algebra 2 factorization. And yeah, that's about it. Thank you guys for watching, and see you guys next time.